All right. So, a lot of you out there are BTS fans already, and now it's time for you to become BST fans. Like what I did there? You can use that. All right. So, one thing I want to talk about is recursion intuition. Because what we're going to do is we're going to code just two things. We're going to code, or maybe three things: how to insert, how to remove, and how to print this thing out. That'll be enough for what we do with this semester. Okay, but to do that, we have to revisit something we visited earlier in the semester, and that was recursion. Okay. Before the summer enrichment thing, we talked about it. So let's see, what's the intuition of recursion? Well, if you kind of remember, we talked about the stairs, okay? And the stairs have a recursive solution, okay? Which means the function can call itself. And the reason the function that solves the problem the stairs can call itself is because, well, if my solution is I take a step up and then call the step function again. So my function is void step. This is really ridiculous, right? And I take a step up, void step. Oh my god, a choke. Okay, let's do this right. Void step. Okay, and I say step up, step up. Oh my god. And then I call step again. What's gonna happen? Well, this person's going to take a step up, and then step's going to be called again, which is going to make this person take a step up, and step's going to be called again, which is going to make this person take a step up, and step's going to be called again, right? And the only thing we have to worry about is when this thing stops, all right? So you might be thinking, hey, that looks like a loop solution too. And it is a loop solution. Anything that you can do with recursion, which is calling a function within the body of the function, you can do through looping. All right, and actually, sometimes it's even better to do it through looping for memory concerns, and we'll deal with that some other time. But for right now, what I want you to look at is how kind of elegant and trippy the solution is, okay? What we're saying is that we're going to take one step towards the solution, and then we're going to call the function again. Okay, and the reason this works in the step case is because, and this is the recursion intuition I want you to have, okay? If you take anything away from recursion, this is what I want you to have, because it's kind of beautiful. Okay, so this is the problem, okay? And if I take one step towards the solution, so I'm down here, and I take one step towards the solution, okay, so the problem was stairs, and I take one step towards the solution, I am confronted with a smaller version of the same exact problem. It's climbing the stairs. And so if that happens, if you're ever in a situation where it looks like you're going to take one step towards the solution and see the same exact problem or a smaller version of the same exact problem, think recursion, all right? So recursion is when things have this self-similar property, all right? One step towards the solution here, I'm confronted with a smaller set of stairs, okay? Now, there was one thing that I forgot to talk about, and that is, where do we stop on this? Okay, well, we stop when we get to the top. So we have to have something called a base case. That's our stopping condition in recursion. Just like we have to have a stopping condition in our while loop, right? We could say, while we're not at the top, take a step up. We could similarly say, void... what was it? Step step class, right? Does anyone take step class? No one can answer me. We're on video. So step up. Wait, hold on. Are we at top? And if so, return. Okay. Otherwise, step up. Okay, so take a step up. Take step up, and then call step again. Okay. So what's going to happen here, and I'm going to write actually what will happen in memory down here, just so that it's clear what's going on. So I'm going to call this step A, and step B, and step C, and step D, and step E. Okay, and the person is right here, and we call the function void step on step A. So we call step A. Okay, and what we do is we say, are we at the top? Well, clearly we're not at the top, so we're going to step up. So this person is now on step A, and then we're going to call step again. So we have not finished the step A function, because the step A function doesn't finish until we evaluate this. Okay, and what are we calling step on? Well, we're calling it on the next step. So assume that the step is passed in here. Okay, step B. This isn't a real function anyways, right? And then step B, what we're getting to is, are we at the top? No, obviously not, right? So we're going to step up onto step B. Okay, and then we're still in step B though, and we are going to call step on C. Okay, and this is going to go on. We're going to call step C. This thing is not at the top, so it's going to jump to the top, the next one, and then we're going to be stuck evaluating step C until step D is evaluated. Okay, and then step D is going to say, I'm not at the top, so jump to the top. Okay, and then we're going to go to step. What's this? Yeah, so step D is going to be evaluated, and then we're going to go to step E. Okay, and it's going to say, I'm not at the top, so let's go to the top, and it's over here. Okay, and then whatever step E calls, I don't know what this would be, but whatever it decides to call on, it would say, at this point would say, I'm at the top. All right, it would hit this condition and return, which would return back to step E, which would return back to step D, which would return back to step CB, right, which would return back to step A, and all of these would complete at that point. Okay, and this thing would be at the top. All right, so what's interesting is this, are we at the top return, okay, is returning before we call our function here. And we could put this in a different order, and it actually might make more sense to you because there was no step over here to step up. That was my bad. What you might do is, it might make more sense if we take the step first and then check if we're at the top and return. Okay, so take step up. This is step. If we take step up and then check if we're at the top, okay, and then return, what will happen is we'll return here at step E, because we'll take the step up and then we're at the top, and so then we'll return back, and that will have evaluated this step for step D, and then D will complete, and then C will complete, and then B will complete because C completed, right? They're all dependent on each other, and then A will complete because B's completed, and we return out of the recursive call. So what happens in memory, right? If you want to kind of remember what's happening in memory, step A is being thrown onto the memory stack. But step A is not finished until step B, which is now thrown onto the memory stack, is finished. But step B is not finished until step C, that's thrown onto the memory stack, is finished, which step D is going to be thrown onto the memory stack until finished, but it's not finished until step E is finished. Step E finishes, step D can finish, step C can finish, step B can finish, and step A can finish. So the reason a lot of people say looping is more efficient than recursion is the idea that we're knocking a bunch of these functions onto the memory stack, okay? And you'll see why that might become a problem, if you have a giant binary search tree, right, and you're really, really being memory inefficient with it. But it's more fun, so we're going to go into recursion. And typically, people like recursive solutions because they look elegant. Like, they're aesthetically elegant, and it's kind of clever. It's like you're not solving the whole problem, you're solving a step and then just calling the function again. It almost seems like magic. So, okay, that's recursion intuition. Let's stop here, ask a few questions, and then we'll come back and we'll talk about how we're going to do insert, remove, and printing out this thing, and then a few programming exercises for you to test your mettle. All right, I will see you BTS fans, and now BST fans, next video.